Every time we make a measurement, there's going to be error. And that shouldn't worry you, actually, because there's always error whenever we make any measurement in the real world. Errors can be classified as 2 or 3 different kinds: systematic versus random. And sometimes we can even classify those third ones as blunders, which is very interesting. So let's start with systematic error. So a systematic error is one where there's basically a flaw in the equipment. So there's some reason that every time we make a measurement, it's a little bit high or a little bit low, let's say. So there's a flaw in the equipment or the design. So the way we have the experiment, maybe we're reading the numbers a little bit higher or lower by poor design, or maybe we are boiling at a certain step for a couple minutes too long and some of our samples evaporating, or maybe we haven't calibrated the pH probe, so, improper calibration. So because we haven't calibrated, all our pHs are reading, say, 0.03 units too high, and so everything is being thrown off, consistently, systematically thrown off. Random is where most of our measurements, most of our error lies up being. So why do I say most of our error is hopefully random? Systematic error can be reduced. And so if the equipment is flawed, either figure out a way to fix it, calibrate it, or do it another way. Okay, design another experiment. Find problems in the procedure and fix them. Don't boil as long. Or maybe use a condenser so that when you boil off your liquid, it drips back in there. Random error is just by essence of living in the universe we're in. There's just constant random buffets of gas molecules or air or antiparticle-particle fluctuations from whatever it may be. I mean, there's just really no way to control this kind of stuff. And so this is due to natural, uncontrollable fluctuations. It can't be eliminated 100%, but by experimental design, it could be reduced. So, for example, imagine that you needed to add 5 milliliters of a particular reagent to your reaction. Well, maybe you're using a 1 milliliter pipette 5 times. And so now every time you make a measurement, right, there's a little bit of error, and by doing it 5 times, that error starts to build up to a larger and larger amount. Well, maybe instead of 5 1 ml samples, you take 1 5 milliliter sample. And so now the random error is decreased, let's say. So we can design the experiment differently to maybe eliminate causes of random error. We substitute one random error that's large with another random error that's low. Or maybe we take 10 tasks and crush it down to 5 with a smaller error in the end of the day. Blunders are things like not following the procedure correctly. So not following procedure. You literally do something incorrect. Not doing the calculations correctly. Basically, you do something wrong. You drop your sample from your, you've weighed it out and you drop half of it on the floor. Maybe you scrape some up. So blunders are not acceptable, really. So if you blunder in an experiment, you really need to start over again. In discussion of errors, I will always ask for a discussion of systematic and random errors. Blunders, you can't just say, well, it's human error, or I did it wrong, or I calculated wrong. That's not a proper source of error. Blunders should be completely eliminated. If you blunder, you just need to redo the experiment again. We talked too about precision and accuracy. So precision versus accuracy comes up a lot. Accuracy is how close your measurement is to the true value. And by true, I mean, how do you know the true value? Well, typically you can purchase materials that are standard reference material. And there's a lot of companies that will produce materials and they will carefully measure it or carefully control what the concentration or the amount is. And they can supply you with, custody of evidence chains and calibration certificates and whatnot. And NIST will sell you these, the National Institute of Science and Technology. So you can buy material that's basically pre-analyzed and guaranteed to contain what it says it's going to contain on the certificate. So a NIST reference material would be an example of something that you could know the true value, and your accuracy would be how close you got to that reference material. Precision is the reproducibility of the measurement, so how close your results are to one another. So if you measure it 100 times, okay, your 100 measurements will all be different from one another, but how close are they? So if they're very close, it would be precise. If they're not very close, it would be imprecise. And this is all a relative term.